Good morning. It is Thursday, March 26th. Please stand for the pledge. No kidding, although we should probably stand for a pledge anyhow, because we haven't done it in a couple of weeks. Uh, I'm going to attempt to give a little bit more explanation on the potential energy diagrams. I kind of went through it quick yesterday, so I'm going to just add a little bit more explanation. I hope the lighting is okay. It's kind of bright windows across from me, so back here it's a little shadowy, so I don't know how the camera's picking it up. Like I know looking at myself in the image of the screen that it's a little dark, so hopefully you guys will be able to make it out best as possible. I talked about the differences in the lines, but there were a couple of questions that asked more specifically about a catalyst and how it impacts this thing. And something else was in there. Oh, the delta H, question number 13. I said I was going to explain. Let me see if I can do these things right now. First off, the catalyst. I'm going to draw one of these diagrams. Okay. The one that I've drawn here happens to be an endothermic, because from beginning to end, it's going up in energy. So that's endothermic. All chemical reactions have to have this activation energy hill. The activation energy hill provides stability to the substance. If there was no hill, we'd kind of be going back and forth all the time. But it creates the need for the effective collision to cause the reaction to happen, so it provides stability. What the catalyst does, it makes these reactions happen more easily, happen more quickly by lowering that hill. So to this diagram, I'm going to add a dotted line that represents the catalyst acting on the curve and changing the shape. Okay? So if I added a catalyst, that would be the hill. That would create changes in the activation energies. These next two arrows that I'm going to be drawing are going to represent the forward and reverse activation energies with the catalyst. Okay, so this dotted line here is going to show the forward activation energy height with the catalyst. This one, wait, didn't go high enough. It's got to go to the peak. Is that it? One more. That looks like it. To the best of my ability to get a line. That represents the size of the, can you see that? That represents the size of the lines for the activation energy for the catalyzed reaction. For the non-catalyzed reaction, these are the solid lines. That's forward, that's reverse, and that would be the height of the line. Again, I'm drawing this freehand. This board is moving as I write, so please excuse that. So in this, looking at question 12, I think, questions 11 and 12 asked about the diagram on page 140. So yes, I guess you should have your books out right now so we can go over the answers to some of these questions. If we look to page 140, question 12, it says which numbered interval will change with the addition of the catalyst to the system. The ones that will change are any of the lines that go. So in my diagram, I drew the forward activation energy and the reverse activation energy lines. Those were lowered. Also, if I put my x-axis on here, okay, the potential energy of the activated complex would also change. Any of the lines that go to the top. So forward activation energy, reverse activation energy, and the potential energy of the activated complex, those would be the things that undergo a change. Delta H, potential energy of products and reactants, which aren't drawn onto here, would not change. Also, question number 16 asked about rate of a reaction. The smaller the hill, the faster the reaction will go. The higher the hill, the longer it will take, because less collisions have enough energy in the reaction to create the product. So in my reaction here, the reverse reaction hill, the reaction going backwards, right? Normally we progress left to right, we call left to right forward. But in the reverse reaction going this way, right, right to left, that has the lower hill, and having the lower hill, that's going to be the faster one. So the catalyzed reverse would be faster. Looking at the reaction diagram, question number 16, the forward reaction has a smaller hill, therefore the forward catalyzed would be the fastest. In mine, since mine is endothermic and the one in the textbook is exothermic, the answers to the question is going to be opposite. Both including the catalyst to be faster, because that's the reason for the catalyst. It'll speed it. But it's the forward reaction which is faster because it's exothermic. Smaller hill and forward. Smaller hill and forward for exo. That's number 16 in your book. Smaller hill in reverse for the endothermic. So it's faster in reverse. Okay. That takes care of the speeds questions. Delta H. All right. Pull a chair because I'm going to talk to you directly out of the book for a minute and then we'll see how it goes. Okay. If we look again on page 140 in your book, you'll see two reaction diagrams. The top one, figure 8-5, is an endothermic, and the lower one, figure 8-6, is an exothermic. They're both kind of the same. They say hypothetical elements, the ones on the left. In 8-5, it's C and D. In 8-6, it's A and B. Those are the reactants because they're on the left. And they form products either A, B, C, or D, depending on which one you're looking at. Let's focus just on 8-5. The delta H, the difference between products and reactants, that difference between products and reactants is positive 20. That means that you have to give 20 units of energy to C and D in order to make them A and B. That 20 kilojoules is the amount of energy that they must gain. So if you give C and D 20, it'll become A and B. If we look at the one below it, right, that's an exothermic one. That means that's the energy released. A and B will create C and D, and then 20 units of energy, the difference between products and reactants being at 100 and 80, will give you C and D, and that 20 units of energy will be released, the difference between the two. The one hard thing about this, if anyone had any questions directly right now, couldn't answer them. Some of you might. I'm going to explain question number 13, and I'm going to send you a link tomorrow to a packet of, they've got like 20 questions. I think they're all multiple choice or most of them multiple choice on the reaction diagrams. I'll send that to you either tonight or tomorrow. I don't know. And I'll go over it shortly before we move into the equilibrium section. Okay. I would like, if possible, to have this unit finished before what our Easter break would be. And maybe provide one more Edmodo test. Figure out how we manage that. But I think at this point in time, all but one person has gotten to take either the original test or the makeup test. If you're that person that it was incomplete on the first test and didn't take the makeup test, get yourself a good internet connection, even if you have to wire yourself in, hardwire it, call your cable company for advice on that, because maybe the Wi-Fi in your house isn't that great, or go to the room where the wireless router is. Take that test there because they do work. All but one person has been able to do it. You can do it if you get yourself into a good position in your house or hardwire your device to the internet. Okay. Where's the point? Okay. I forgot where I was going. Okay, I was going to go look at question 13. I'm sorry. It says potential energy diagram below of a chemical reaction. Okay. There's the diagram, question number 13 on page 141. It says, what is the difference between the potential energy of the reactants and products? Okay. If you look, the reactants, that's the start, those are at 20. Your best ability to estimate would put the products at about 40. So we actually have a formula for delta H. I'm going to write it down because you're going to notice sometimes they're positive and sometimes they're negative. I think I directed your attention at one point in time. I believe it's reference table H or I. We're not talking about that reference table just yet. So when we do, I'll direct you to it. But one of them gives delta H's. I know we've looked at it because we've talked about the value of delta H being negative, and at the bottom of that table, there's a note that says, please note, delta H values are negative for exothermic reactions or something like that. I don't remember the exact words, but you can go find that table and read it. We'll do more about that table later on. This one turns out to be positive because I'm going to write down that formula for delta H for you. Actually, I think it says it in the footnotes on the right column on page 140. It says there's note 1 and note 2. Okay, so maybe I'll even write a summary down about that on the little board here. All right, the formula for delta H is equal to HP minus HR. That's an R. Products minus reactants. So in this one, our products were at 40. Our reactants were at 20. Delta H is equal to positive 20. These delta H's, by the way, the sign is always associated with it. So if it's a delta H value, it's going to be written positive. H is enthalpy. Enthalpies are only going to be positive. The change in enthalpy can be positive or negative. And if it's the delta H, they always write the positive with it. They don't just write 20. It's generally considered positive 20. Although they didn't put a sign on these in the choices for number 13. They really should have. But I guess they're looking for just the difference between them. So if they ask you for a value of delta H, you're going to see the signs. That's in that reference table. I forgot if it's H or I. We'll see it eventually. All right. So the answer to number 13 is 1. Let me go over the rest of them on these 2 pages. All right. We'll look to start equilibrium next week. Maybe finish it up, and I'll give you, I think it's like 80 review questions for the test, which I'll go over, and I'll try to assign that test by Wednesday, not next week, the following week. I'm still trying to keep my practice, giving you a week's notice or more of when we're going to be taking a test. So I see myself finishing the kinetics portion, the reaction diagrams, and the speed today, and then finishing equilibrium towards the end of next week, going over some practice questions, and then a test Tuesday or Wednesday. Not sure which day I'm going to do it. I'll probably post it early on Tuesday so you can take it either Tuesday night or Wednesday. I'm going to do it in the same fashion. I'm going to do it on Edmodo. Please try and get it right. It's going to be timed the same way the other one was. I don't want to have to do a retake test for you, because if I do a retake test a second time, I'm going to maybe average the 2 tests or something. Like some of you I know had trouble. It was the first time through, but I can't keep putting up retake tests because, you don't know the procedures for, taking the test right now. This is what we got to do. If there was another way for me to get you to do it, I don't even know. So you're going to have to bear with me and, work to the best of your abilities. I will say this, on that first test, I have 45 students in chemistry. 40 of the 45 were able to do it without problem. The 5 people that did it, 4 of the 5 actually took the retest and got a higher grade. So we'll figure it from there. Let me go over these, starting on page 140 with question number 11. Which statement correctly describes the reaction from start to finish? 2 is high, right? 3 is lower. Where 3 and 4, where 1 and 2 is high. Where 3 and 4 is lower. So it's going down from start to finish. That's an exothermic reaction. We can also look above at the reaction. It says A plus B yields C in energy. The word energy is on the right. Both those things indicate that it's an exothermic reaction. And in exothermic reactions, heat energy is released. Okay. I think I said to you before that the answer to 12 is 2. Catalyst would lower the hill. So any of the intervals that reach the top, like line number 2, which is the forward activation energy, that would decrease. 13 we said was choice 1, 20. 14. I think I might review all the lines for you. Okay. 1, I'm going to actually write down its abbreviation. Bear with me a second while I wipe my board. Okay. PE of products gets abbreviated heat, which is enthalpy. Enthalpy is a potential energy. Heat of the product. So HP means potential energy of products. PE of the reactants is heat of the reactants. They never used the enthalpy symbol for the activated complex. They simply always just call it potential energy of the activated complex. They never use H activated complex. Don't know why, just never seen that abbreviation. I guess it's legitimate. Never seen it used. So, in labeling the diagram in question number 14, 1 would be HR, heat of reactants. 2, delta H, triangle H. That's the difference between the products and reactants. 3 is the answer to our question. Activation energy goes to the top. Since it's from the product side to the top, that's going backwards. It's right to left progression instead of our usual left to right. And then 4 is Hewlett-Packard. No, HP, heat of the products, potential energy of the products. Right? Number 15. Wait, I said the answer was 3, did I not? Which hour represents heat of reaction? Oh no, I am actually I am wrong. It's 2 is heat of reaction. I thought it asked for reverse activation energy. Heat of reaction is the same actually for forward and reverse. The only difference in the reverse, it's exothermic, so it's negative. In the forward, it's positive, it's endothermic. But it's the same interval. I saw the word reverse. I thought it said activation energy reverse, which is 3. So 14 is 2. I did define the lines for you. And again, if you have any questions on these, post, comment, something. You know I go back and read it. Okay. 15. Hey, what's the answer? You think it out for a second, then I'll tell you. It's Shakespearean. You know what that means, right? The answer is to be or not to be. It is not the question. In fact, it isn't the answer. Okay. C, line C. See how it goes to the reactant height just above the letter A? C, that's forward activation energy. It goes to the top. It's an activation energy. And A and D are the enthalpies, the potential energies. A is HR, heat of reactant. D is HP. 16 we said it was the forward catalyzed, which was 1. And 17. In the potential energy diagram below, which hour represents the potential energy of the activated complex? That's C. Okay. B is delta H. A is potential energy of the reactants, which we call HR. And D is potential energy of the products, which we call HP. Okay. Let me answer questions 1 through 10. I think the kinetic stuff was easier, the rate stuff, but we don't know. All right, starting with question number 1. As the number of effective collisions between reacting particles increase, the rate of all reactions, forward or reverse, will increase. Choice 1. If you have more effective collisions, you're going to have more reaction. Okay, which of the following pairs of reactants will react most quickly? Okay. I don't like this question. The answer that they're looking for is choice 1, but I'm going to add to it in solution. Okay, because it's a little ambiguous this way. If it was solid sodium chloride and solid silver nitrate, they would react very, very slowly. if they were liquefied, and it doesn't refer to that anywhere in the question, if they were liquefied, they would be the fastest because they're ionic. Just given the rest of this, choice 2 would probably be the fastest because hydrogen chloride will ionize in water and form ions, but in general, it's the ionic in solutions that's the fastest. That's what we're told even within the confines of the text. So I'm going to have you understand that it's choice 1 because sodium is a metal, chlorine is a nonmetal, silver is a metal, and nitrate is a nonmetal. They're ionic compounds. They'll react immediately. Okay. In the reaction, as the surface area of magnesium increases, that means you can use like a solid cube of magnesium or powdered magnesium. The powdered has more surface area, the rate will increase. So as the surface area increases, it means it's being powdered. So the answer is 2. Number 4, consider the following equation. As the concentration of A increases, the frequency of collisions with A and B will increase. If you have A and B in a container, if you add more A's and B's are going to collide. A's will collide with A's, but there are more A's available to collide with B's, so you'll get more reaction rate. Number 5, the rate of reaction can be decreased. All right, so we want to slow the rate of reaction. Okay, so if we increase 4, the volume of the container, so here's your container between my hands. If I spread my hands apart, there's more space. The molecules don't collide, so the rate will decrease. In the stem of the question, under the little diagram of number 5, underline that word decrease. All right, so if you increase the volume, they spread out, it slows down. Number 6, fastest rate, circle 4. Powders have the greatest surface area. They're just comparing particle sizes there. Number 7, raising the temperature speeds up a reaction by, it does 2 things. I talked to you about that yesterday. They collide harder, they collide more often. It's frequency of collision and the effectiveness of the collision, which is 3. Frequency is how often, effectiveness is how hard. 8, which statement explains why increasing the temperature of a chemical reaction, while the others are, the reacting particles have more energy and collide more frequently. That's basically the same thing. That's choice 1. 9, if the pressure on gaseous reactants is increased, the rate of reaction will increase because there is an increase in 3, concentration. So if there's more of it around to collide, they'll collide more often, greater frequency of collision. And the last one, which factor will have the greatest effect on the rate of chemical reaction between, all right, see the silver nitrate here, it says AQ, which means in solution. I think that was left off that other problem, giving the state of matter, which is important. All right, so silver nitrate, aqueous, and copper solid, okay. Molecular mass is not going to affect rate. That you can't even change the molecular mass of a compound, all right. We can change the temperature. Increase in temperature will always speed the rate. And increase surface area of the copper because that's a solid, but that's not a choice. But we can change the concentration of that solution. Okay. Pressure is not going to work here. You know why? Pressure only affects gases. So since neither of these is a gas, the answer is 2. But if it was a gas, 1 would be a viable answer as well. Okay. Look for some practice questions either later on today or tomorrow. I'll give you a review of those on Monday and then move into the next topic on Tuesday, which is equilibrium. It's kinetics and equilibrium. It's the second half of this topic. Okay? Have a great day. Bye-bye.